Okay, thanks very much for the invitation. It's a great honor to be here on this occasion. I'd like to talk about some work with these colleagues. Claudio is in the audience, but I'll mention them as we get into the talk. Maybe I could just say a few words. Over the years, people sometimes ask me, what is it like to be a student of Varadhan? It's a very difficult question. So it's a very easy question because you can just say it's just wonderful. Okay, but more careful answer might be just enjoyable learning. There's always a lot of learning and appreciation for how to try to be light and think a little bit more in a light way about the problem and how to solve it, and also to be very concrete. And so, anyway, it's hard to really answer that question, but it's I had some opportunity just in the past year or so to actually work again or to start a project with Varadhan. And for those who don't know, this is his office. And so I've given this talk several times, and I think people in the audience, many people have heard this talk before. And so I thought I would try something different today. And but this is on the archive if people are interested. Okay, so there's a lot of interest in giving physical meaning to SPDEs of various types, and on the one hand, we're also interested in extending the theory of hydrodynamics and understanding what sort of equations, evolution equations, come out of hydrodynamics in various settings. For instance, if there's a external random environment present. And so in this work, there's two aims. So we're going to consider something like a Sinai type random environment, which I'll say exactly what it is in just a few minutes. And in this environment, the environment will survive in the hydrodynamic scaling, and there will be a random term that appears. And so the PDE normally, which would be a deterministic PDE, would have a random term. So it would be a SPDE, and it'll be something of this type. And this is a singular SPDE because this product is troublesome. So if you, for instance, if you just take the gradient through, then this is so W prime is a spatial white noise. Okay, and so this will have some irregularity of this type, -3/2 minus, and rho, because of the equation, the type of equation, the parabolicity will go up by 2, so it'll be -1/2 minus. But then when you multiply them, you're getting something with negative regularity, so it's a singular object. So okay, so the way we'll try to approach it is actually through two steps. We'll motivate that we should perhaps try to regularize this random environment. The random environment will have it's very chaotic in a certain way, and so we'll try to regularize it, smooth it out a little bit, and then take the hydrodynamic limit, and then we'll get an equation, and then we'll look at the limit of that equation as a parameter goes to 0. Okay, and also at the end, I'll mention also something about the motion of a tagged particle. How does that, what sort of SDE does it follow in the limit? Okay. All right, so let me just talk a little bit about some previous literature. When the random environment is ergodic enough, allowing enough movement, then there are a lot of works actually which derive limit PDEs. The terms in the PDEs will have some homogenized deterministic terms, but which will reflect something to do with the random environment, but there'll be deterministic PDEs. And so there are a lot of works. Even we quote a paper by Jeremy and Patricia Gonzalez and Milton Hara and so forth. Okay, and but there are only a few where the random environment actually is strong enough to survive in the scaling, and most of these are with respect to exclusion, symmetric exclusion, or sometimes asymmetric exclusion. This paper is about asymmetric exclusion, or independent particle systems. And so the hydrodynamic equation that you'll get will be something of this form, and W will be something to do with the realization of the noise. Alpha, usually the traps are something to do with alpha stable distribution, so it'll be alpha stable subordinator. Okay, so the SPDE that we'll derive, you can consider in terms of its literature, you can consider a more general equation. So here I put a different function, and so this is a nonlinear equation. And if you introduce u so that the gradient of u is rho, then you can integrate the equation. You get this one here. So this is analogous to this would be like the KPZ equation. This would be like the stochastic Burgers equation. And so if you didn't have this, if the functions weren't functions of nabla u, gradient u, then and if it's just u, then this would be what's called a generalized parabolic Anderson model. Okay, and that was one of the examples that was considered in this seminal paper, Gubinelli, Imkeller, and Perkowski. And more recently, Bayol, Debush, and Hoffmanova gave a little bit simpler proof. Okay, and so the equation that we'll consider is having a gradient of u instead of u inside, and so some of the estimates will be a little bit different. Okay, so also this is coming from, hopefully from the physics. So this will be some sort of mass conserving, some mass conservative equation, and so that's also a difference. Okay, so here's just a simple cartoon of what we're trying to do. I don't know how useful it would be, but so let's just so we'll be working only in dimension 1, where the these previous the solution of these equations will be actual functions. We'll be looking at lots of particles, and they'll be interacting in some way. I'll mention the interaction. It'll be we're going to choose a zero range type interaction, and let's this is some sort of cartoon of the environment. This will be some sort of polygonal path process for or partial sum process for some IID random variables. And so, so if the slope is positive, then there's a small, if you're here, then there's a small nudge to the right, and if the slope is negative, there'll be a small nudge to the left. And anyway, so the particles are all subject to this environment, and so you can see that you can get trapped a little bit. Okay. So so let me try to describe carefully what the environment is that we're going to actually put in the system. The Sinai random environment is not exactly what we're going to put, but it's the starting point. Okay, so just to remind you, so just think of IID random variables indexed on the lattice. UX is between 0 and 1, and the log of this, and also bounded away from 0 and 1, and the expected value of this log is 0. So here's you could just take this as an example if you like. Okay, and so if you look at a random walk moving in this environment, let's say Rn is the position at time n, then so the transition of the random walk to go to the right is, let's say, 1/2. Yes, it's exactly ux. So if I just took this example, okay, very good. Okay, so it's known. So this is a result of Sinai that the scaling is not moving so much. It's trapped quite a bit. It's on this log n squared scaling. And in that scale, you're going to some non-trivial limit, and because of this log, there's no non-trivial functional central limit theorem for this object. So as I mentioned, this Wn that we had in the cartoon is, let's say, the partial sum of these increments. Okay, so this is one point. Okay, so what would be a continuum analog? It's this is all classical. It's it's Brock's diffusion. So if you consider this diffusion, W prime is again a spatial white noise. Of course, this is not well defined. This is informal, but it has the same sense as the discrete evolution. Okay, more carefully, one would be able, one defines Brock's diffusion in terms of a scale and time change. So under this scale, the diffusion is a martingale, and then you change the time. Okay, so Brock's showed, that this actually may be a candidate for a continuum version under this log t squared scaling. It went to the same limit. These are all annealed results, averaged over the environment. Okay, so coming now to the environments that we'll put on. So to connect Sinai random walk with Brock's diffusion, Senurel considered some environments which are scaled, which have a scaling parameter in them. So now Rx are just IID mean zero finite variance, and so form the same sort of combination that we had before. Divide by square root of n, however. Okay, and we're going to and then. Yeah, I'll mention how we're going to speed up time in just a second. So we have the same sort of picture for how the random walk is moving. So let's speed up time diffusively. So square of the coarse graining. So 1 over n. The bond edge sizes are going down like 1 over n. So let's speed up time by n squared. So if you look at this combination with these environments. In the averaged annealed sense, you're you're converging, you have a functional center limit theorem to Brock's diffusion. Okay, so we're going to put those kinds of environments in the background. What's the interaction of the particles? It's these zero range interactions. Okay, informally, what's going on is that every location has a clock. The clock will ring at a rate which depends on the number of particles. So there's some background function, little g, and our notation will be that eta of x is the number of particles at this location. So in this case, three particles. And so with rate g of that number of particles, one of these particles is allowed to jump, and when it jumps, it will jump according to it'll go to y with this probability. Okay, so the particle that moves over is just chosen at random among these particles. Okay, so this is what we mean by zero range. Okay, and so if you put all that together, then so we have a generator for the process. Okay, and so notation is that this is the updated configuration. So eta is just a list of in one dimension. It's just a list of numbers which tell you how many particles on each location, and so this is the updated one where there's one less at x and one more at y, and this occurs with this rate. Okay, and then we out over all the possibilities. Okay, so independent particles are part of this. If g of k is equal to k, then you can think each particle has its own exponential one clock, and the minimum is exponential number of particles. So it's so independent particles are a case of zero range, the zero range process. If the underlying function little g is g of k is equal to k. Okay, so we're going to work in one dimension. In fact, we'll work on the one-dimensional torus. So it's an increasing torus, and so that's mostly for technical reasons. Okay, and so let's try to see what the hydrodynamic limit is. Okay, so we're looking at a nearest neighbor process where jumps are only to nearest right or nearest left, and they the probabilities are given by this let's say initially by this Seigneurel environment. Okay, so let's define the empirical measure. This is if you would integrate this with a test function g, something like the indicator of an interval, then this is just the average number of particles in a scaled set, and we expect that this empirical measure should converge to rho t rho dot comma x dx as t varies. So it's a trajectory of absolutely continuous measures. This is what we're expecting. So there's some rho that this is the asymptotic mass density that we're looking for. It has an evolution. How do we calculate the evolution? Let's just apply Ito's formula. This is very standard, so let's just do a few calculations. So we just take the stochastic differential, we apply the generator to this object, and Mn will be the martingale that comes out of that. So if you do this calculation, there's some, the environments had this, where is it? It has this, the dominant term is 1/2, right? So there's some small perturbations, but dominant term is 1/2. So so the 1/2 part gives you something to do with Laplacian. after you sum by parts a couple of times. Okay, and this will be the rate of that jump, of jumping. Okay, and so the drift part, you can only do it by once, sum by once, and so there will be a gradient that is introduced. Okay, so it's just this is the hyperbolic part, if you like, and so this is what emerges after the calculation. So I remember the environments where Rx divided by square root of n. There's an n squared that we put here, and there's an extra 1 over n coming from this derivative. So you everything will cancel if I multiply and divide by square root of n, but this is what I have to deal with now. Okay, so intuitively, this is giving the equation that we want, although it's extremely formal. So if x is, if you think of x as scaled macroscopic point little a, then you can rewrite it in terms of the partial sum process. If you go through all these, just first order Taylor, and and if you homogenize the background function little g, it should have some homogenization. So this should be something like this, and the martingale is going to go away because it'll be of order 1 over n. So we should. This is the equation that is somehow controlling the continuum density. Okay, so but this is doesn't make any sense. So because can't differentiate Brownian motion. Okay, so let's adopt. So this is the motivation for smoothing out. So let's smooth out the environment. So what I mean by smoothing out the environment is let's consider Qx, which is the average of the variables R in a small macroscopic box. So just minus n epsilon around x. So this will be just this average, okay, and this epsilon, let's just fix it for the moment. Okay, so let's consider these environments. So this is in some sense cheating, but let's see what we can get out of it. Okay, so we could also convolve with smooth kernel and also define Qx that way as well. Okay, so instead, if you went through the calculation that we had before, so this was the troublesome thing that we were trying to deal with before. If you put in Q instead of R, and you went through all the business, then we're because we averaged, when we take the derivative, we're just getting this kind of epsilon is not going to 0; it's fixed. So this is the object that we get, and let's just declare that this is what we call W prime epsilon. Just give it a name. Okay, so is that okay? Is that clear? If you use the convolution with that kernel, then you would get this type of expression here. So the regularity of this is now C1/2 minus, and this can be as smooth as we want depending on what psi is. Okay, so let's have a statement of quenched convergence first. Okay, so informally, this is what we expect. So we're gonna put now these environments in the background, and the hydrodynamic evolution should be governed by this equation, where this is now okay for us. This PDE is well defined, and the annealed one, when you average over, will get you the law of this object with respect to the underlying Brownian motion. Okay. Let's see. To make a careful statement, let's just say what the assumptions on the underlying function is. We assume some positivity here so that particles can move, and some sort of growth rate condition, as well as some condition where you have if you graph the function g, then it's between two lines like this. Okay, and so under this assumption, it's known that the process has very good mixing properties, and that'll be useful in the proofs. Okay. There are a lot of zero-range process has nice invariant measures. One of the reasons to try it. So the invariant measures will be these certain product measures which have marginals like this. So the marginal of probability of k particles is given by this, where phi is a parameter, and so g of k factorial is g of 1 times g of 2 all the way up to g of k. So if g is if g of k is equal to k, then this is just Poisson. So these are like product of Poisson-like measures, and because of the random environment, these parameters, sometimes called fugacities, have to satisfy some relations between them. So they're respecting the underlying random environment. Okay, so they're linked in this way, and so you could just multiply it through by a little constant c and still maintain this equation. So there's a whole family depending on c. So that's something what we expect because there's mass conservation in the system. This function phi that we had in the PD that we're going to derive is also has expression in terms of these measures. So it'll be essentially the mean jump rate with respect to one of these invariant marginals. Okay, so initial conditions. So we can start from fairly general conditions. The initial conditions should be something which has a law of large numbers associated to it, as well as some relative entropy bound with respect to one of these invariant measures. We could also just state that we should just take this one, which is you just put some number of particles at each location independently. The number of particles at location x, the mean number of them is given by this a priori function. You take a function rho naught, and then according to this sampling, that should be the mean number of particles here. So this is sometimes we call this a local equilibrium. Okay, so we can start from a measure like this, and so let's put everything so that everything's on the same space. So by Skorohod representation, let's just make it so that the polygonal paths will converge in a probability 1 set to the Brownian motion path. Okay, and so in the Quenched results, of course, we're picking a representative from that probability 1 set. Okay, so anyway, so Quenched hydrodynamics. So with Landim and Pacheco Carlos is at Srinivasa in Mexico City, and Jianfei Shui, who's was a postdoc at Arizona, but he's accepted a position at Soochow University in China. So this is a more careful statement of quenched hydrodynamics. So we're converging to rho, which satisfies this equation. Remember, epsilon is fixed positive, so this is a well-defined PDE, and it'll be the unique solution in a certain class of weak solutions. And I haven't put down what the class is here; it's too long. Okay, if you're interested in annealed behavior. So under averaging, the process measure of the empirical measures will converge to okay, at a specific, let's say, you could do it for the whole trajectory, but here I guess I've just stated for one time t. Okay, so or you could just think of this as dot. Yeah, it'll go. Yeah, so it'll converge to that trajectory. Okay, and the law of that trajectory will be with respect to this Brownian motion. Okay. So so let's now get the singular PDE out of this. Okay, so we're using the para-controlled apparatus of Gubinelli, Imkeller, and Perkowski, and I debated how much to put here because the notation is very long. Okay, so the main problem is that this product is not well defined, and so but you can write it in terms of paraproducts, and then there will be a certain fixed point problem that one can define where the solution of the fixed point will be a solution of this equation. And anyway, so we have convergence as epsilon goes to 0 to the unique solution given by this fixed point, this para-controlled version. It's local in time, so a priori there could be a blow-up time, and so up to the blow-up time, one has this convergence, and it's convergence in probability with respect to the realizations. Okay, and but for this particular equation, one can improve this, and this was done recently. This paper shows that actually the solutions exist for all time. This is on the torus. That's another complication. Gubinelli, Imkeller, Perkowski were on the line, or in two-dimensional space actually. So they're, yeah, I should have said that. Their parabolic Anderson model was in 2 dimensions. Okay, and and also Bayul, Debouche, Hoffmann also was in 2 dimensions. And so the differences is that we're in 1 dimension, but we're considering this conservative equation with gradients of solutions appearing. And and we're on the torus. So we have to, this is technical work to bring things back to the torus. So there's some slightly new things in getting the gradient as so I've written the equation for the gradient here, but if you would lift it to u, which is the gradient of u is maybe this solution here, then you would have the gradient of u here, and so there's some things to do there as well as to deal with putting it onto the torus. Okay, so so maybe let me talk a little bit about tag particle. So what is the tag particle problem? It's just were there any other questions here about this? Okay. So the tag particle problem is we just just color one of the particles and then we follow its behavior. So this is we can write down its evolution. So remember, so in the zero range, the clock here rings with rate little g, but then you have to select at random one of the particles, and so this is the rate at which the colored particle moves over, and it'll move over right or left depending on this on what the Q is, and so I guess I could have had another, one-line explanation for this. So it'll be 1/2 plus this, and then there's to go to the right, and then 1/2 minus this to go to the left. Going to the left comes with a minus sign, so the halves cancel, and you had Q going to the right, and then you had minus Q going to the left, and so when you put them together, you get 2. Okay, and so and then there will be also a martingale term coming out of this. Okay, so this is the thing that we want to try to analyze, and so one can kind of guess the answer, and the guess turns out to be okay. So if you would just postulate that this converges to a path. So here in this first part, we're also doing this in 2 steps. So epsilon is positive in the first part. So epsilon is fixed positive. And so let's just say we postulate we go to this path. This path should satisfy this type of limit here. So this is just coming from here. So after we scale time diffusively, divide by n, take the limit. The Q was something, remember that this W prime epsilon appeared there. I guess I'm skipping a few calculations. I'm sorry about that. So we get that this VT should satisfy this equation, and the martingale also one can compute. The martingale has this quadratic variation in the limit, and so that's our so this is work in progress with Marcel Houdani is a student at Arizona, and Claudio. So this is the first part. So we're able to get that this thing is converging to VT satisfying this equation. So in other words, this SDE. Okay, and okay, so this is well-defined SDE, and when G of k is equal to k, phi of alpha, phi of argument is equal to argument, and so from here this thing just goes away. This is just 1, and so you're just getting back some sort of smooth version of Brock's diffusion. Okay, and it's not too, at this point, for this particular model, taking epsilon to 0 is not so hard, and you can recover Brock's diffusion. Okay, but we can also do it in the more general case. So using the para-controlled convergences, so in this limit, epsilon is going to 0. And so you're getting the thing that we should get. So this is so we get this this SDE, and the way to do it, I think SDE experts we just look at the scale of this diffusion and then show that the scale as epsilon goes to 0 goes to the scale of this equation. and then just invert the scale. Okay, so this is not too bad. Okay, so when we started out, we really wanted to work we were really thinking about Seigneur environments, and not doing two-step, but just going directly. So that's an open question. So that's a potentially nice question that we'll look at. We have some partial information. So under these kinds of environments, so the original ones, not the averaged ones. So the original Seigneur environments, we do have some information. So if you look at the the annealed mean of this quantity, so if G is as I said, if G is an interval, this is just the average number of particles in an interval. This thing will converge to the expected value of. So remember, rho naught is what we started from initial profile, and so there's some translation with respect to Brock's diffusion, and so the annealed means are given by this, and so this is in the independent case. I should also say that. Yeah. So this is when little g of k is equal to k. So okay. Proofs are. Yeah. Are we done? Okay. All right. Proofs are. This is the last slide. So I think I've already mentioned the proofs here. The proofs here. There's some inhomogeneities which have to be dealt with. Okay. Thank you very much.